Today, we are going on a journey not just into a piece of hardware, but into the very frontier of human ingenuity to understand the graphics processing unit, or the GPU. In the early days of computing, graphics meant a white square bouncing across a black screen in a game of Pong. The math was simple. But as our digital dreams grew, so did the demand for raw, unfiltered calculation. Fast forward to the sprawling, hyper-realistic vistas of Cyberpunk 2077. To render a single frame of such a game, a computer must decide the color, brightness, and reflection of millions of pixels, 60 or even 144 times per second. This requires a level of computational throughput that defies human comprehension, tens of trillions of calculations per second, TFLOPS. If you try to do the work of a modern RTX 4090 using the billions of people metaphor, you would actually need several thousand Earths worth of people all calculating in perfect unison just to render a few seconds of gameplay. This staggering scale is the foundation of modern visual culture. It is the difference between a drawing of a fire and a simulation that understands how every spark flickers and every shadow falls. This story is a journey of two halves. First, we are going to act as microscopic explorers, shrinking ourselves down to the size of an electron to navigate the physical labyrinth of a graphics card. We will walk through forests of transistors and cities of silicon, exploring the architecture of the GA102 die. We will see how these physical components are birthed in sterile labs and why perfection is a myth in the world of manufacturing. Second, we will shift from the physical to the metaphysical. We will explore the soul of the GPU, its computational architecture. We will learn why a GPU can mine Bitcoin or train an AI to write poetry, while your high-end CPU would struggle to keep up. By the end of this journey, you won't just see a video card. You will see a masterwork of human engineering that bridges the gap between abstract mathematics and the vivid reality of your digital life. To understand the GPU, you must first understand its brother, the CPU Central Processing Unit. Think of the CPU as a state-of-the-art fighter jet. It is incredibly fast, incredibly agile, and can handle almost any mission you throw at it. If you need to jump from a word processor to an operating system task to a complex logic problem, the CPU zooms there instantly. It's the brain, designed for serial processing, doing one very complex thing after another with lightning speed. The GPU, however, is a massive cargo ship. A cargo ship isn't fast in the way a jet is. It can't turn on a dime, and it doesn't handle varied missions well. But what it can do is carry 20,000 metal containers across the ocean in a single trip. If you have 20,000 separate math problems that all need to be solved at once, the fighter jet, CPU, would have to fly back and forth 20,000 times. The cargo ship, GPU, just loads them all up and moves them in one go. This is the parallel philosophy. The GPU doesn't care about doing one thing fast. It cares about doing a million small things simultaneously. Let's step inside the flagship of the previous generation, the GA102 GPU die. At its heart, this chip contains billions of transistors, tiny switches that are so small that thousands of them could fit on the head of a pin. But these transistors aren't just scattered randomly. They are organized into a strict Roman-style hierarchy. The chip is divided into graphics processing clusters, GPCs. Inside those are streaming multiprocessors, SMIs. This organization is key to efficiency. Within these SMIs, we find the specialized workers. There are CUDA cores, which handle the heavy lifting of general math, tensor cores, which are the geniuses of artificial intelligence, and ray tracing RT cores, which are specialized architects designed solely to calculate how light bounces off surfaces. This division of labor allows the GPU to be a multi-talented beast, handling beautiful lighting and smart AI upscaling, like DLSS, at the exact same time. In a perfect world, every chip coming off the assembly line would be a masterpiece. But we live in a world of dust and entropy. When silicon wafers are printed, even a single microscopic speck of dust can ruin a section of the chip. In the past, these broken chips were thrown away. Today, engineers are smarter. This process is called binning. Imagine a baker makes a huge tray of cookies. Some come out perfectly round and golden. These become the RTX 3090. Others have a slightly burnt edge or a missing chocolate chip. These become the RTX 3080. Instead of throwing the burnt ones away, the baker just trims the edge and sells them at a lower price. In GPU terms, if a chip has a few broken cores, NVIDIA, or AMD, simply disables that entire section of the chip and sells it as a lower-tier model. This is why you can have 5 different graphics cards that all use the same physical chip design but perform differently. It's a beautiful lesson in making the most of imperfection. If we zoom in even further, past the clusters and the multiprocessors, we reach the CUDA core. This is the fundamental unit of the GPU's power. It is a compact, elegant arithmetic calculator. Its primary job is an operation called fused multiply add, FMA. Think of FMA as the basic building block of the universe's math. Whether you are calculating the trajectory of a grenade in a game or the gradient of a neural network, you are mostly just multiplying numbers and adding them together. Because a single GPU contains thousands of these CUDA cores, it can perform these FMA operations at a scale that seems supernatural. It is the strength in numbers strategy taken to its logical extreme. One ant can't move a log, but 10,000 ants can move a forest. The GPU chip itself is the brain. But like any brain, it needs a body to survive. This is the graphics card, the PCB. When you look at a card, you see the massive fans and heat sinks. These are there because all those billions of transistors switching on and off generate an immense amount of heat, enough to cook an egg in seconds, if not for the cooling system. Surrounding the chip are the voltage regulator modules, VRMs. These act like a high-tech power substation, taking the raw, dirty electricity from your power supply and cleaning it into a precise, steady flow that won't fry the delicate silicon. And then there's the VRAM, video RAM. If the GPU is the chef, the VRAM is the kitchen counter. It holds all the textures, models, and data the chef needs. If the counter is too small or too far away, the chef has to wait and your frame rate drops. Communication is everything. To keep the GPU fed with data, we use specialized memory called GDDR, graphics double data rate. We are currently seeing the transition from GDDR6X to GDDR7. To get more speed, engineers use multi-level signaling like PAM4 or PAM-3. Think of it like a highway. Standard memory sends data like a light switch, on or off, 0 or 1. PAM4 signaling is like a dimmer switch with 4 different brightness levels. This allows the memory to send twice as much information over the same wire in the same amount of time. For the ultra-high-end AI chips used in data centers, we use HBM, high bandwidth memory. This involves stacking memory chips vertically on top of each other, like a skyscraper, right next to the GPU. This eliminates the commute time for data, allowing for throughput speeds that can exceed a terabyte per second. Now, let's look at the logic of how a GPU thinks. Most GPU work follows a principle called SIMD, single instruction, multiple data. Imagine a drill sergeant, the GPU shouting "drop and give me 20" to 1,000 soldiers. Every soldier does the exact same push-up, but they are all individual people. In a game, when you move your character, the GPU has to move millions of vertices, points in 3D space. Instead of calculating each point one by one, the GPU gives a single instruction, move 5 units left to thousands of points simultaneously. This is SIMD. Modern GPUs use an even more flexible version called SIMT, single instruction, multiple threads, which allows the soldiers to handle slight variations in their tasks without breaking formation. It is the ultimate form of organized mass production. To manage this mass of soldiers, the GPU uses a strict chain of command. The smallest unit of work is a thread. A group of 32 threads is called a warp. Think of a warp as a small squad. The SM, streaming multiprocessor, doesn't manage individual threads. It manages warps. If one thread in a warp needs to do something different, this is called divergence. The whole warp has to wait for it. It's like a group of friends walking down the street. If one person stops to tie their shoe, the whole group has to slow down. High-level GPU programming is all about making sure no one has to stop to tie their shoes, keeping the data flow as smooth as a river. You've likely heard about GPUs being used for Bitcoin mining. But why? Mining is essentially a giant global lottery. To win, you have to solve a mathematical puzzle that is very hard to solve but very easy to check. Because a GPU has thousands of cores, it can buy thousands of lottery tickets every second. For a long time, GPUs were the kings of this game. However, eventually humans built ASICs, application-specific integrated circuits. If a GPU is a cargo ship that can carry anything, an ASIC is a specialized pipe that can only carry one thing, water. An ASIC can't play Cyberpunk, but it can do hashes 1,000,000 times faster than a GPU. This is why the mining craze on GPUs eventually faded. The specialist outperformed the generalist. We are currently living in the AI spring, and GPUs are the soil from which it grows. Why? Because the math behind ChatGPT, Midjourney, and self-driving cars is almost entirely matrix multiplication. Imagine a giant grid of numbers multiplied by another giant grid. This is what tensor cores were born for. While a standard CUDA core does one multiplication at a time, a tensor core can multiply entire grids matrices in a single clock cycle. This is why AI has advanced so fast in the last 5 years. We didn't just get better software. We built hardware that was hardwired for the specific math of intelligence. When you see an AI generate an image, you are seeing tensor cores performing quadrillions of matrix operations in the blink of an eye. As we emerge from our microscopic tour and look at the graphics card once more, it looks different, doesn't it? It isn't just a hunk of plastic and metal. It is a testament to what we can achieve through collaboration. Thank you so much for joining me on this deep dive today. Wishing you all the very best of health and happiness. And if you found this journey as fascinating as I did, please consider hitting that subscribe button and ringing the bell so you don't miss our next adventure into the heart of technology.